Hi, everyone. I'm Jeremy Snyder with the Molecular Foundry Communications team, and I'm here for a conversation with Emory Chan, who's a staff scientist in the Inorganic Nanostructures facility. We're here to talk today about some of his exciting research on avalanching nanoparticles and robots that can help accelerate the pace of discovery of new materials. Emory, can I have you introduce yourself and tell us a little bit about your work?
Hi, my name is Emory Chan. I'm a staff scientist in the inorganic facility in the Molecular Foundry. So, in my group, we study inorganic nanoparticles, how to make them, and what we can use them for. For example, making them into tiny little light bulbs or flashlights or lasers.
Awesome. Okay, so can I get you to explain a little bit just what an upconverting nanoparticle is, what the basic concept is?
So, a nanoparticle itself is a tiny little rock that's anywhere from 1 to 100 nanometers in diameter. And so, an upconverting nanoparticle will emit light when you shine light on it. Now, most things, when you shine light on them, they might glow a little bit. So, these are kind of like glow in the dark nanoparticles, but they tend to glow in colors that are lower energy than the light that's incident upon them. So, red light is lower in energy than green light. So, if you shine green light on something, then you'll get red light.
Okay,
So, an upconverting nanoparticle is a type of nanoparticle that can emit light with higher energy than you excite it with.
got it.
So, these don't actually break the law of energy conservation. What actually happens is that you're taking two photons or two particles of light that have lower energy and combining the energy into a single emitted photon.
So what's the practical point of something like this, other than it just being interesting?
Well, one of the main applications of these upconverting nanoparticles is for biological imaging. So when you look at your hand, you can't see through it because the visible light that is bouncing around the room is also bouncing off your skin. It's scattering off
Mm,
your skin or it's being absorbed. But infrared light, so light that's longer than the red, for example, 650 nanometers, can actually go somewhat through your skin and your tissue.
got it.
And so this is really powerful, except for the fact that up until recently, the kinds of cameras that you needed to observe this kind of light were very, very expensive and very specialized. They're not
Got it.
actually what you would have, for example, in your phone. And so upconverting nanoparticles allow you to have the best of both worlds because they emit visible light, which we can all see, but they're excited by the infrared light.
Whoa.
Um, th-
So you can basically illuminate them with this frequency of light that easily penetrates tissues, but that you can't necessarily see, and then they will, upon receiving that light, turn it into visible light, so that you're basically getting visible light out of invisible light.
exactly.
That's awesome. Okay, so we have these upconverting nanoparticles, which are capable of turning invisible light into visible light with all these useful applications. Can you explain a little more what your breakthrough with avalanching nanoparticles is and why that gives them a whole host of new abilities?
So an avalanching nanoparticle is a highly nonlinear material. So that means if you double the power of light on the material, you get 2 to the 30th times more light out. So that's about a
Wow.
billion times more light.
That's fascinating. So these particles have basically a property where as the light intensity on them increases, their output increases really dramatically, so that like differing intensities of light create really discrepant responses.
Exactly.
So I know that these avalanching nanoparticles are really useful in microscopy because they help you get around something called the diffraction limit, which is basically the smallest thing that you can see with light, which is related to the actual physical size of light. How is that possible? How do these nanoparticles help you get around the diffraction limit?
So normally when you excite material, you're focusing a beam spot of light down upon it, and the width of that beam spot, the diameter of that beam, is about half the wavelength of light that you're using. And
Got it.
so the particles will emit light that look like essentially a spot that has that same diameter. Now, these particles have this very interesting capability where actually their emission profile, their emission beam spot, is actually 70 nanometers instead of that 500 nanometer diffraction limited beam spot that you'd expect.
Wow. Okay.
And the reason they can do that is that a normal beam spot in a microscope, the intensity in the center is greater than the intensity of light on the edges. And if you remember, these particles have the unique capability where a very tiny difference in the power that's incident upon them leads to a huge increase in the power of light emitted. And so the particles in the middle of that beam spot will emit far more light than the
Wow.
particles on the edges.
Interesting. So because of that, like that differing response to only slightly different intensities of light, you can basically shine, a relatively wide beam on these particles, and they will shine back a very narrow beam, which allows you to get a way higher resolution when you're looking at them.
Exactly. It's like you basically converted your flashlight into a tiny little nano flashlight.
Wow, that's so cool.
Another factor that's great about this technology is that we're exciting in the infrared. So, unlike the other techniques which use high energy photons, such as ultraviolet light or electrons, that can be very damaging to tissue and biological samples, our technique uses infrared light that not only transmits through tissue and biological materials, but also it's not as cytotoxic, so you're not killing live cells, and it's also not exciting as much autofluorescence, so we don't get as much background.
Wow, okay, cool. That's awesome. So it seems like a really powerful tool and across a lot of different use cases. Can you tell me a little more about how you guys discovered this material and developed this?
Well, that's a really interesting story. So, we've been studying upconverting nanoparticles for over a decade at the Foundry. And one of the interesting properties of these particles is that their optical luminescence properties come from their dopants or the ions that are put inside of these
Cool.
nanoparticles.
Okay.
And these ions can interact with each other in very complicated ways so that their properties are greater than the sum of their parts.
Got it.
But that makes it complicated to predict what will happen when you combine them together, or you
Sure.
don't know exactly which combinations of these ions, which compositions will actually work. And so it's a game of making these nanoparticles by trial and error, and that can be very tedious. It can take,
Mm.
months or years to find the right composition. And so one of the approaches that we've taken in our accelerated discovery theme is that we utilize robots that can synthesize these nanoparticles in parallel. So I developed a robot called Wanda that can synthesize up to 96 different nanoparticles in parallel instead of making one or two types of nanoparticles in a given day.
Wow.
And so that allowed us to build these huge data sets that can not only allow us to find the optimal compositions of nanoparticles very quickly, but also we can build models that can then allow us to predict the optimal compositions instead of having to make them.
So because the properties you're after arise from these kind of synergistic combinations of ions and like things that you infuse into these materials, it is really hard to predict under normal circumstances. But one way you can get around that is just by making every combination and seeing what they do.
Exactly. And so these robots are one of the unique capabilities of the Foundry.
That's so
So
cool.
people come from around the world to use them. And we had high school students and undergrads that would make all these different combinations.
Cool. So it simplifies the actual like operations involved there to the point that you can then just expand out like who is capable of doing this work.
Exactly.
Wow.
So when we were trying to find nanoparticles that could be excited through tissue, we then took these models that we had developed from our robotic data sets, and we just asked the computer, okay, go run a bunch of simulations and tell us what are the optimal compositions for exciting at this very common infrared wavelength of 1064 nanometers.
Wow, cool. So by creating this massive kind of combinatorial, set of different combinations, you can create basically just a database that you can then go type in like, oh, I need these two properties and
Right, yeah, or it
wow,
has predictive capabilities as well. So
that's awesome.
most of the discoveries that we make in our group, we have performed the simulations and kind of understood where are good regions of compositional space before we even go into our robots. And our robots, instead of mapping out the whole world, which it's still fairly slow to do that in a
Yeah.
robot, know exactly where to focus. So even if our understanding is a little bit off, which is pretty common when you're trying to discover entirely new physics, you can still rapidly refine that into into the exact right nanoparticle.
That's awesome. Are there any other like capabilities other than light emitting that that these upconverting particles can be used for?
Well, a lot of their basic properties come from their light emission, but beyond just looking to see if they glow, another powerful application is the fact that high energy light like UV light or blue light can perform chemistry, right? So you could use that for catalysis, you could use that to make or break bonds.
Oh,
Um,
cool.
but of course, if you're trying to do that in tissue or a brain, you don't want to use even higher energy light to produce that UV or blue light. So in our case, we could shine infrared light into an organism, and then the light would hit the nanoparticle and produce UV or blue light
Oh,
and
wow.
actuate some sort of process. So we've
Huh.
had users at the foundry develop molecules that could release nitric oxide, which is a therapeutic.
That's
Or
so cool.
there's other papers shown by our users and collaborators that this optogenetic actuation via infrared light can essentially stimulate neural activity.
Wow. So even if your goal is actually to like, to introduce light that is high energy enough to disrupt systems or chemically alter things, then you wouldn't want to shine it through, kind of from the outside, so it's much more effective to shine it from the inside.
Exactly.
Wow, that's so
Right. So
cool.
it's kind of a remote control for these nanoparticles that are inside an organism.
That's fascinating. Such an interesting kind of tale of an advanced kind of accelerated method of discovering new materials, discovering new possible applications of it, yielding such a useful product. That is about as much time as we have. Thank you so much for talking to me today and telling me about your really interesting work. I look forward to seeing comes out of the inorganic facility in the future.
Thank you so much.